Okay, so algebra, today we're in 5.6. There are 7 sections in the chapter. Today and tomorrow feel very related to each other. We're going to take what we've learned about writing equations, and we're going to talk about how it is used with real-world data. Fitting a line to data. As you know, in doing science experiments in your labs and things, I'm sure that you have found that sometimes the data doesn't form a perfect line, right? Maybe you're going to find that in your science fair project this year. You're gathering data about some topic, and it looks almost like a line when you plot the data on a graph, but it's not a perfect line. Who here has seen that before with data? Good. We're going to see that in some of the data presented to us today. And so when you take the information that you have gathered in an experiment and you start plotting it, you're looking for what might happen, right, in the future if you continue the experiment. What's going to happen? And so when you plot it and it's not a perfect line, we call it a scatter plot. Well, when you plot it and it looks like anything, we call it a scatter plot. It's just simply a bunch of data that's put on a graph to see if there's a relationship between the pairs of data. And what we're looking for is a correlation. So I had a student last year do a study using swabbing the desks around here. Do you hear all the coughing going on? Swabbing the desks, putting it in little, what do you call them, petri dishes, and seeing what would grow there. You know, is there a lot of bacteria? What are there viruses? What is growing on things? And so, and testing different surfaces, he found that certain places had more things going on than others. Okay, it's interesting. If a surface has been cleaned, probably there was less bacteria in that area. And if a surface hadn't been cleaned in a long time, then maybe there was more. He was looking, where do we see a relationship between a particular surface and the amount of stuff that's growing? It's interesting. So a correlation, we have a relationship between two data sets. And we have 3 possibilities. We could have a positive correlation, a negative correlation, or no correlation. A positive correlation is when y increases as x increases. This is going to be easier to see down below where we have a graph of it. Who could define then a negative correlation? If a positive correlation is y's are increasing as x's increase, it looks somewhat like this, like a positive line, right? A negative correlation would be, Sophia?
Maybe y tends to decrease as x increases.
Well, y tends to decrease as x increases. So as the x's are increasing, the y's are decreasing, so it has this kind of a negative look to it, okay? And then no correlation would be as x's increase, what? What do y's do if there's no correlation?
Same.
Stay the same, or they might increase, they might decrease. Y's might do anything. We don't know what they're going to do, actually. There's no trend seen. So this is what it looks like in the form of a graph. So here's the data right here. I'm moving the lines out for a second. Okay. Here's the data. It's just little points that have been discovered and then plotted, right? And notice that they're not a perfect line, but these points in this graph tend to go down as x increases, right? So we call this a negative correlation. When the points tend to go up as x is increased, you see how it looks like positive? Like you could put a line into that data, which is what we're going to do today. We're going to say if you could take and fit a line in there as best you can to kind of model that data. Now we can write an equation of the line, right? And maybe that points are sometimes falling off the line, but it's pretty close to what you see in the data. Same here, we might have a negative line. Okay, but notice the no correlation set. We have points as x's increase, y's are just doing all kinds of things. There's no rule here that we can make. We don't know what the next point will be. If I go out here to where x is 10, is the point going to be up here? Is the point going to be down here? I don't know. They're all over the place, right? There's no correlation. Okay? A line of fit shows the trend of the data. So this is the new term today, the line of fit. You're just fitting a line, like I did here, into the data to show the trend. Okay, you don't need to write this down. We're just going to look at a picture of some data from your textbook and describe the correlation of the data. So here we have the hours of studying versus test scores for a group of students. And so what type of correlation do we all see here?
Positive.
Positive. So that means that as people do what? Who can describe? Study more, their test scores tend to go up. That's what the research shows. Do you believe that? Yeah. The more time you spend doing something, probably the better you are at doing it, right? And notice this piece of data. What type of correlation?
Negative.
So the more hours of television you watch, the lower your test scores are. And probably this, in 2013, we would say the more hours of media time that are filling your life, right? It's not just TV. As a matter of fact, if you're like my kids, you even watch TV shows when you want to using Hulu or something like that, right? Who does that? Who watches shows like when you want, you just bring them up like that, yeah. So that would count, right? The number of hours you're spending doing that would definitely affect, I guess, test scores in this case, right? Using the scatter plots, in example 1, predict a reasonable test score for 4.5 hours of studying and 4.5 hours of television watched. So what do you think a reasonable test score would be? Everybody jot it down. What do you think your test score would be based on this table? You can see it in your book too. For 4.5 hours of studying and for 4.5 hours of television watched. And what do you see? What do you think a reasonable score would be, Abby?
For 4.5 hours of
She says for 4.5 hours of studying around a 70. Who agrees? 70? 71 or something? Good. And how about for 4.5 hours of television watch? What do you see, Ray? About what? And as I'm looking here, 4.5 would be right around here, right? Lower 70s maybe, right? Or mid 70s, maybe. Isn't that interesting? So look at this. Jeremy's question was interesting. If you really wanted a high test score, how about watching just 1 hour of TV and then you get a high test score, right? That's what this says. 1 hour TV, 90. Would that work for you? 1 hour TV is like the way to go. It's a perfect way to get a 90. Or, Jeremy, what do you think? Probably these people who are putting in less TV time are these people who are putting in more study time.
I don't understand how 8 hours of study.
Let's write an equation for a scatter plot. Let's do it using this data and then we will write the steps down so that you have kind of the method to it. But here's a set of data. You're going to have to pause and take it all down. Okay, so we're going to plot this data. And so each of these are points, right? We're going to walk 1, fly 3. Walk 2, fly 5. Walk 3, fly 8. Walk 4, fly 9. Oops, I see, we have a scale of 2. Because look at that, the data goes all the way to 14. So walk 1, fly 3. Walk 2, fly 5, 2, 4, 5. 3, fly 8, 2, 4, 6, 8. Notice I have a scale of 1 on the x-axis because these values don't go further than 8. But I have a scale of 2 on the y because these values go above 10. Oh. And where am I at? Walk 5, fly 1, 2, 3, 4. Fly 9, 2, 4, 6, 8, 9. 5, 2, 4, 6, 8, 10, 11. 6, 2, 4, 6, 8, 10, 12. And 8, 2, 4, 7, 8, 2, 4, 6, 8, 10, 12, 14. Okay. So if we're asked to write an equation for the data, what are we going to have to do next?
Find the rise and
Well, we don't know which 2 points to use if we're going to like find a rise over a run. So this is where we fit a line into the data. So I'm grabbing a line and we're going to use our best art, right? It's a positive correlation, yes. And I want to write that's not the question though. The question is, can you write the line? See that? So I'm going to fit a line into the data. And when you do this, you want to see about half of the data on either side of the line, right? And it looks like this line is kind of showing that. So fit it in as best you can. And now when we write the equation, we're going to ignore the actual data. We're going to ignore the red points, and we're going to write the equation of the line that you see here. And so we need 2 things, don't we? We need slope and we need a y-intercept. Or we need slope and a point. So we can write this equation. So let's see if we can find that. Okay, so let's try to write this equation. Ultimately, we want to find slope, and as Tessa said, we need the y-intercept. Do we see the y-intercept right here? You see it? Do you want to say that we actually have identified it here? Where is that?
2.
Based on our scale, it would be 2, right? So we could say 2. Now, if it was somewhere between the intersection on our little graph here, we might use a point somewhere else, point slope form, to write the equation, right? But here it looks like it's about at 2, so we'll use 2. And then we need to find the slope. So if we're saying that this is right at 0, 2, where do we see another place where it's crossing right at a corner of 2 blue lines? Do you see that? Can you see
The big red one.
it almost, you think right here?
No, no, no.
Right here?
The biggest no.
Like the
biggest
biggest,
dot right
yeah.
here? I think that's at an intersection of a corner. I almost think this one's
That
that
one is.
right here. Or even that one there, huh? Okay, so let's use that one. We're going to just look for the rise and the run. So this is really approximating the way we're doing it here, isn't it? And what is the rise?
10.
2. Yeah, 2, 4, 6, 8. So we have a rise of 8 and a run of 1, 2, 3, 4, 5. 8 over 5? Interesting. And now, wait, just a second, Chris, we're going to write the equation. Since we found these 2 things, how would we write the equation? What form would we use?
Slope y-intercept.
Y equals mx plus b, slope intercept. So let's write it. Y equals
8/5 x plus 2.
plus 2. Okay. Be super careful if you're using a different scale in your y direction than in your x direction, right? Okay, you're not using the data in the table to find slope. You're using the line that you've drawn. And we were looking for places where the line crossed right at the intersection of the graph paper, right? So we could see that this point here was at 5, and in the y direction it's at 2, 4, 6, 1, 2, 4, 6, 8. Oh, I'm sorry. It's at 10, but it rose from the y-intercept 8, right? It rose 8, and we ran over 5. So that's how we got the slope of positive 8/5. So the key, the book says that the graph of this line is at y equals 1.6 x. What is our answer here in decimal form? It's exactly 1.6. Do you see that? I mean, 5 goes into 8 one time, and the remainder is 3/5, which is 6/10. So we were able to find the same exact slope that they did when they did this using a best fitting line. And their y-intercept they have is plus 2.3. Are we close to 2.3 with our y-intercept?
Yeah.
So we're within reason, okay? So the steps to doing this, writing an equation for a scatter plot are make a scatter plot with the data on a graph paper, right? If there is a correlation, draw your line of fit. And then step 3 would be use the line of fit to write an equation. Locate 2 points on the line of fit so you can find M and write your equation using point slope or slope intercept, whichever form you like. And don't forget in step 3, when you write your equation, you are not using the data from a table. You are using the line that you drew. That's where you get the slope and a point, not from the table. Okay? Okay, you will need graph paper because you are going to draw the line to write the equation for today. So have fun with some graph paper.